All right, continuing on in chapter 15, we're going to start looking at the things that we did in 251 and 252, but now how those things translate into three dimensions. So 15.2 is limits and continuity. So we're going to look at what a limit would be like in three dimensions. We're going to talk about something called the two-path test, and we're going to look at continuity of surfaces. So let's see here. What we're going to do a lot of times is we're always going to kind of start back in 2D and think about what this concept was in 2D and how that's going to relate to what we're talking about now in 3D. So let's think about a limit and say, for example, we've got some function f here, and we want to look at what happens as we go towards some point A. And that point could be defined or not defined. In this case, it's defined. But remember, when we're looking at a limit, it doesn't really matter if it's defined or not. All that matters is what happens as we approach that point coming from the left and coming from the right. So walking along that graph, are we getting close to some output? And are we getting close to the same output from the left and the right? So it's again that we're making, how far away we are from A as small as possible, and we're getting closer and closer to L. So that's what it means for our limit to exist. And so our definition in 3D is written down below here. We've got function f and it has a limit L. And so instead of just going, getting closer and closer to some value A, we're going to get closer to some point AB, because remember we're talking about this three-dimensional function where we're plugging in that ordered pair and we're getting out a single value, our height, our Z value. So we're going to be looking at what happens as our XY ordered pair gets closer and closer to that point, that specific point AB that we want to look at. Sometimes we write it as P is our standard XY point and P sub 0 is that specific point. And for our limit to exist, that as we get close to AB, as we approach AB, then we're going to get our outputs, our Z values, are going to get close to L. So again, the thought is, okay, well, what does this mean in three dimensions? So, if we have some sort of surface, it'll draw here. Say we've got, this is our surface. Okay, so some sort of, just random surface sitting out there, and thinking about, what does it mean for us to approach the point, I don't want the point XY, I want the point AB. So what does that mean that we're approaching AB? So AB, here's A, say there's B, and we can kind of think of where that's sitting in the XY plane. And if we go up to our surface, we're hitting right here. And we want to think about, okay, we've got our Z value here, and it's what we get from f of AB. If we're defined there, again, we definitely could have a little hole in the surface there. But we want to think about, what does this mean that we're approaching that point? So when we're in two dimensions, we can approach from the left or the right. Well, unfortunately, here in three dimensions, we can come close, from that direction, from that direction, from that direction. We could take a squiggly path and go towards that point, or we could take, something that looks like a little bit more exponential or something. There are an infinite number of paths that we could use to approach that point. So that's going to make this a little bit tougher when we're talking about, thinking about, does this limit exist? Because we are, kind of thinking about it on that surface. We're coming at it from that way, the squiggly path along our surface. So it can be any of those paths. And we have to make sure that all of those paths come to the same Z value, that we don't have a surface where we've got, a spot up here, maybe think about it as a cliff, and then a spot down here, so that as we come, along from this path, we end up way up here, and as we come from this path, we end up way down here. So we want to still try to avoid those situations that we have in two dimensions. So Now the question is, okay, what kind of things are in our toolbox that we can use to help us figure out when we need to, what we need to do, how we're going to figure out if these limits exist or not, especially if we have infinite paths. So let's think about an example here to start with. So we've got the limit as we're going to 0, 0 of x squared times y over x to the fourth plus y squared. And this is a pretty standard kind of question that we want to look at. When we plug in the point 0, 0, which we still should check that. You should always, with any kind of limit that you're taking, plug in the point that you're getting close to and see what happens. Well, this one we're getting 0 over 0, so that's not the most helpful. That may mean that our limit exists. It may mean that it doesn't. It may mean that there's some algebra that we could do to help us figure this out. But what we could start by doing is looking at some paths that we could take to approach that point. So one of the paths that we could take to approach this point, so again, if we've got x, y, and z here, one of the paths that we could take is along the line x equals 0. So that is essentially the y-axis. So the line x equals 0, or the y-axis, that is a path towards that point. So if we're thinking about that path, that's a path where x is equal to 0. That would be looking at the limit as not xy, because we're going to be looking along a specific path. We're going to look at what happens as that path 0y approaches 0, 0. So how this changes things is this puts in a 0 for x, because we're staying along that path where x is always 0. And this comes up with 0, because we get 0 over y squared, and it doesn't matter what y is unless it's 0, but we're doing a limit, so we're getting close to y being 0, but we're not actually going to get there. So this limit is 0. We would get the exact same thing if we looked along the path of y being 0, right? We could write that out really quick. Oops. If I could get my handwriting under control. If we looked at the path where x was changing and x was just getting close to 0, but y was being stationary as 0, that would change our limit to look like this. And we would still get 0 over x to the fourth, which would be 0. So we start to think, cool, I found two paths where I'm getting the same thing. Sweet, maybe that's what's happening here. And so we can kind of keep trying paths. We could look at what's happening as we approach along the line y equals x. That's another path. If we stay on that line, that's approaching that point 0, 0. So that would change our limit to, we could say x because y is equal to x. And we could think about, okay, when is that approaching 0, 0? So how that would change our limit is our y's would all turn into x's. And this would leave us with something that we could do a little bit of algebra with to see what our limit is. Let's see, what do we get on the top? We've got x to the third. On the bottom, we could factor out an x squared. And we've got the limit as x goes to 0, 0. And we're going to get x on the top and then x squared plus 1 on the bottom. And what we've done by doing that little bit of algebra, canceling our common factors on the top and the bottom, we've turned this into one that we can plug 0, 0 in, or 0 in for x, and we can actually evaluate it. And just like we did with the ones up above, and we get 0. So now we're like, okay, now I feel like we're really rolling. We've got 2 or 3 paths where we keep getting 0. Well, another path that we could take, let me get a different color. Let's get blue here. Another path that we could take would be y equals x squared. So let's see if I can draw that path. It would look like that. Y equals x squared. That's another path. That 0, 0 is along that path. So basically what I'm doing is picking any path, or you can think of it as a graph or an equation that's in the xy plane that contains the point 0, 0. So maybe we'll write that all paths must contain the point 0, 0. So for example, y equals x squared plus 2, that would not be a path we would be looking at. not a path we would consider because the point 0, 0 is not on that graph. So we're only looking at graphs in the xy plane that have 0, 0 as a point on them because that's a path that we can take through that point. So looking at y equals x squared, we can replace y in our ordered pair with x squared. And that's still going to 0, 0. So again, what that does is it changes our y value here. Our y values are now all going to be x squared. So we're going to have x squared on the top times another x squared, x to the fourth plus x squared being squared. So ooh, how does this simplify? X squared to x squared is our path, and 0, 0. So we've got x to the fourth over x to the fourth plus x to the fourth. This is very interesting because we get the limit x squared. This is the most annoying part of limits is you got to keep writing limit out. X to the fourth over 2x to the fourth, that is, oh no, that's 1/2. So we have a problem. We found a path where we got to a different limit. So what this tells us is this overall limit that we have, the limit as xy goes to 0, 0, x squared over y, x to the fourth plus y squared. This does not exist. And it's because we went from a direction and we got to a different place. So it's like in 2 dimensions when, you come from the left and you get here to 0. Say, for example, you get to y equals 0 and you come to from the right and you get to maybe, y equals 2. So it's that idea of as we come from the right and the left, we're not meeting up in the same place. And the same thing has to be true when we're talking about these 3-dimensional limits, that as we follow any path that we can take to get to the point 0, 0, that xy point, we have to get to the same z value. Because if not, then this is essentially what's happening in 3 dimensions. All right, so what this does though is this gives us a really nice way for us to prove that limits don't exist. So this gives us something called the 2-path test for non-existent limits. So this says, if your function approaches 2 different values, so 2 different, and maybe we'll put in there z values, 2 different outputs as your ordered pair approaches that point along 2 different paths in the domain, then your limit does not exist. And that's really all it takes. You've just got to have this situation where this was the problem. Even though we have 3 other paths that are going to the same z value of 0, we've got one path there that's going to 1/2. So that means our limit doesn't exist. And the problem is too that we do have to find if we do have that path that doesn't exist. Now we're going to hopefully keep these fairly straightforward so that it's pretty easy to see when that happens. And looking at along the x-axis and the y-axis and x equals y, because a lot of times we do go to the point 0, 0. Those are going to be the paths you do want to start with. But those are things that we can talk about too when we're looking at this in class. But what is nice, because it's going to be hard to prove that these limits do exist because there's infinite paths. So what's nice is a lot of things that used to be true about limits in 2 dimensions, they're still true. So like if we have the limit of a constant function, so say we have basically a flat plane sitting up in 2 dimensions, if we've got the limit of the constant, it is a constant. If we've got a linear function, basically that z is equal to x no matter what, then we just get to do direct substitution. We can plug that a value in for x. Same if we had our function was z is equal to y, then we could just plug that y value in, and that would be what our limit's equal to. And we've got even more. So these limit laws here, again, I don't want to run through all of them. This is from your textbook. You can read through them. But basically what this does is between those last 2 that we had and the sum, difference, and constant multiple, this gives us all of our polynomials. Oh, I guess along with product would also be in there because you could take x times x and that would give you x squared. Um, So this is giving us that all of our polynomials are limits. We can do direct substitution. It's going to give us all the linear, the planes. I always want to say linear functions, but they're planes. It's going to give us, all of our sines and cosines, things like that. Square roots, as long as, oh no, that's a power function. There's our square root. There you go. And as long as our limit is positive, if we're taking a square root or a fourth root. So all of those limits that used to exist and everything that was fine, if we just had cosine of x plus sine of y, those we can do direct substitution on. So all of those things that were true in 2 dimensions, they're still true here in 3 dimensions. So that's the main thing to remember about this. Um, I had a list of sort of our no worries functions. So things that are no worries, those are our polynomials. It's always good to look at your notes sometimes. Sine, cosine, odd roots, and e to the x. These guys have domains of all real numbers. Everything's great with these. Our troublemakers are the same troublemakers that we have when we're talking about domain, and they're still going to be troublemakers when we're talking about limits. So when we have rationals and we're dividing by, we're looking at where we've got that division by zero. Sometimes there's going to be some algebra that we can do to get rid of common factors on the top and the bottom. So those are going to be things that we want to look at. Tangent functions, those have places where we're undefined. So it's these ideas of looking for when things are undefined. Are even roots, right? Those are sometimes problems because we get square roots of negative numbers and those don't exist. And natural log. Okay, so these are kind of the ones to really pay attention to when we might have some interesting situations where limits don't exist. But if we've got our no worries functions, then we can just do direct substitution.